All right, so let's see. So I was talking about this homogenization result. I have a couple of slides about the proof that I can show you really fast, even though we sort of did the calculation already. Okay, so remember that we have elliptic operator equals data with given boundary data. And we have something that we think should be an approximate solution. And we computed in the previous lemma that it actually is an approximate solution. So what did we actually learn? We learned, this is roughly speaking, but this is, you can basically prove exactly this, that if you take the difference with the true solution, then you get the right-hand sides cancel except for the O of epsilon error, which is under a divergent sign, which is what you would expect to be under the divergent sign. And the boundary data is perturbed by O of epsilon. So the way that you really handle this is that the way that I like to handle it anyway is you split the boundary data perturbation. It's just a separate problem from the right-hand side perturbation. And you split it off by just solving the problem with exactly the boundary data perturbation. Okay? And then you can estimate how big this Z epsilon is, because this is really making O of epsilon sized wiggles on the boundary. And so you can just take a test function. You know that like for example, if the A would be symmetric, then this guy by Dirichlet's principle is going to be some energy minimizer. So you can just write down a guess for the solution, which kind of just cuts off the layer, and you can estimate the energy of that as being square root of epsilon. And so you get that by energy comparison or whatever. And then when you subtract it, you see that this function, which is now the true solution minus the approximate solution minus the boundary thing here, now has no boundary data and has the divergence of an O of epsilon. And so you can estimate this just by multiplying by the solution and integrating by parts and using Cauchy-Schwarz. And you get that this thing has H1 norm bounded by constant epsilon. And so you get this estimate. And so I've estimated both the boundary term and kind of the right-hand side term, which is this. And now by the triangle inequality, you see that you can get U epsilon minus W epsilon without the Z, because you can use the triangle inequality. Okay, so I think I even wrote that. So this is by the triangle inequality, and you end up with this square root of epsilon, which mainly comes from that term, which is the boundary layer. And finally, you can go from the W to the U by noticing that the W epsilon is just the U with some wiggles attached, and you can just estimate the size of the wiggles and then more triangle inequalities, and you're done. Okay, so that's what I was intending to get to this slide at the end of the last lecture. But are there any questions about that?
One question. The divergence, this O epsilon term, how large is that?
So what I mean is that I have a divergence of something which is of order epsilon in L2.
After you take divergence, it's same order?
Oh, but when you have a right-hand side of an elliptic equation, you want to measure it in H minus 1, because so this equal sign is in the sense of H minus 1. So you should always use the H minus 1 norm. And if you have something under a divergence, the H minus 1 norm of the whole thing with the divergence is the L2 norm of what's inside the divergence. So then if you want, the H minus 1 norm of this equals exactly the L2 norm of the O of epsilon term, which is just O of epsilon. Yeah, equals. No, equals.
If it's divergence free, for instance.
Yeah, you have to mod out by the divergence free fields. Yeah, that's right. You have to mod out by the divergence free fields, but but otherwise it's equal. I learned from the Evans PDE book that H1 can be represented by this, right? So if you write this in the smart way and you don't put extra divergence free terms in there, then it's actually equal. Yeah, that's what I learned from the Evans PDE book. Okay. Actually, I relearned it because I just taught the course, so I got myself all confused on that point, actually. Okay, so now what was I saying before? All results in periodic homogenization can be proved like that, and the all here should be taken with the quotes, but it really means almost, most of them, unless you find a problem where you kind of actually break the periodicity somehow, which makes it interesting. Most of the things that you want to homogenize can be done like this. This regularity that was assumed is not necessary, because you can do a little interpolation. If you have a U that's not as regular, you can smooth it up. You have an error due to the mollification or whatever, and then you use the irregularity of the smooth guy and you triangle inequality, and you can then recover the correct estimate for any U. And a really interesting question to ask, which will take us into the next part, is where did we use periodicity? So I unfortunately put the answer, but where was periodicity used? Because you can ask at this point, and it's like, because can you do this for any coefficient field? Well, no, because if your coefficient field had kind of had a macroscopic structure, then no. So where was it used? It was just used to solve those little problems on the torus. In fact, if you can solve those little problems on the torus, or if you can find solutions like that which have little wiggles and do the right things, then you don't need periodicity. You just need to be able to solve those corrector equations. Okay, those equations for the phi alpha. So if you have a way to define the phi alpha, you can prove homogenization even without periodicity. The proof that we did was better than the previous ones because it's quantitative. The previous ones, usually like the ones that I was sort of criticizing, are hiding a lot because they use a sort of soft compactness arguments where understanding and explicit dependence of constants go to die. So you have some like bicompactness, you're done. And this one has no step like that. I mean, you can estimate all of these constants very explicitly. It's going to come down to essentially what's the Poincare constant for your domain and things like that. Okay, and you see that the proof is just the same as the original ansatz, which is nice because if you have a nice physics proof, usually you want to make your physics proof the same as your math proof. You don't want to, if you have a, you know, if you need to go to the physicist and say, I have a really counterintuitive proof of your conjectures using very complicated math, then you should have a good reason for that. Otherwise, you should just try to do it exactly what they do. Okay. So now let's talk about the homogenized matrix, because now when I talk about the homogenized matrix, I mean the leading order term of the truth, the full homogeneous sort of macroscopic operator, this thing I was calling script A of epsilon. The leading order term is just this divergence form constant coefficient operator. Maybe you should have a minus, which is essentially the Laplacian. If you do it, if A bar would be symmetric, and then you could do a change of coordinates and you would find Laplacian. If A bar is not symmetric, then shares the same set of solutions with something that is symmetric, because you can put the divergence through the A bar, and then you have A bar contracting against this Hessian, which is a symmetric thing. So it'll be symmetric anyway, just not in its flux. So it'll share the same set of solutions as a symmetric operator. And that means it's essentially the Laplacian. But what is the A bar? How do we compute it? Because if this is the leading order, you know, if this sort of tells us at leading order what our solutions are looking like, then we should try to understand it physically or understand what it's telling us. Well, if you look at just the first order corrector equation, and you're supposed to average some very particular thing that we had in formulas back there. But if you specialize to the case alpha equals 2 and you make a matrix, then you can talk about what the matrix does when it hits a vector E. And what it'll do is it will be the average of the flux. So the matrix A against E plus grad phi E. This here is the gradient of a, okay, so yeah, so why do we write A plus grad phi E? So I should have written the first order corrector equation. So maybe Jean-Christophe wanted me to use the blackboard. So maybe I'll get to use the blackboard now. The first order corrector equation, if you really, if you write just it explicitly, you get this. It's A against E. Okay, so this is a matrix, this is a vector, I'm picking the divergence. You can put this on the other side and write it like, okay, and so this thing you should think of as kind of being approximately an affine function with approximate direction E, and there's wiggles around the E. So it looks like this. Okay, this is the direction, this is the affine function E dot x, and this thing which is wiggles around the affine will be E dot x plus phi E of x. Okay, so it's kind of a corrected affine function, and it's an exact solution of the equation. Okay, so yes, so that's what that is looking like. So the A bar, what does it mean? I said an elliptic matrix is a way of going from gradients to fluxes. It's like the constituent relation. So this is in some sense the average constituent relation for the first order corrector. So it's saying if you want to make kind of asymptotically a solution with this slope, then the average flux per unit volume is this thing. It's going to be A bar E. Okay. What bounds can we prove for it? Well, we can prove the same bounds that we proved or that we assumed for the matrix A of X. Okay, and the proof is nice. It's like if you find the best proof, it's 2 lines. So let's see the proof first of this. And it's also nice to ask, when does equality hold? Because it tells you something kind of physically about what this quantity says. Okay, so the proof of this is, it should in some sense be, we're doing some kind of averaging, right? So something is being averaged. And so this should be Jensen's inequality, basically, because if I had a uniform bound, then it should get better. Well, so I start with this. I say it's less than that because this thing in here is a periodic function with average E, because the grad phi E has average 0. So if I put in here a function with average E, I'm gonna have an inequality like that. And now I can say, because my matrix A of X is always dotted against the quadratic form from my matrix is bounded below by lambda, I have this inequality by assumption. Now we can use the equation, because I'm doing an average here. It's like an integral on the torus, right? And so I can integrate by parts. And if you take this gradient and integrate it over, you get exactly this equation that I wrote, and it kills it. And so you can kind of integrate this gradient over. And because I'm on the torus, there's no boundary condition. And so this term with the gradient, this should be a plus sign. I think I wrote a dot. Okay, so the term with the gradient here is dead, and this E is a constant, so it can go outside the average, and I end up with this. And this is E dot A bar E. It's a very funny. It's very funny. So you can see that equality.
It's much funnier.
Yeah. So equality holds when, wait, it's much funnier than. Okay. You're getting feisty over there. Okay. So equality holds if actually there's no corrector, right? So if the corrector is doing anything, then you will have equality, but otherwise not. Okay. So in some sense, the A bar is going to have a better lower bound for its ellipticity than the A did, unless the corrector happens to totally vanish. And if the corrector vanishes, then you're actually basically dealing with a constant matrix anyway. Let's look at the other proof. Okay, so I moved this one up here. Now we're going to do the other direction. So now there's always this duality between gradients and fluxes. So if you have a proof of something for a gradient, then that means the upper bound or whatever should be proved by the same proof, but for the fluxes. So here's the 3-line proof with the fluxes. You start with this thing, which is what you want to lower bound. And okay. Yeah, so I'm at the end of the day, I'm going to plug in E is equal to A bar inverse E, and you're going to see that's what I'm going to get what I want. But so I start with this, okay, and using the same kind of Jensen, I have this where this GE now. I think I wrote it on a previous slide, but I think I went too fast. So the GE is just shorthand notation for the fluxes. So I have A and I have E plus grad phi E minus A bar E. So this is like the difference between the flux and its average. So I'm going to add in there that sort of mean zero thing. This was a constant, so it's going to get bigger. Now I can use the assumed lower bound on A bar or A inverse as a quadratic form. So I can write it like this. And now I'm going to use the fact that this thing is just the flux, because this goes on the other side. And so this comes here. And you see I have 2 A's, so one of the A's kills the A inverse, and I end up with just this, which is again the sort of quadratic form for the corrector, which we already showed up here was equal to E dot A bar E. So I get this bound. This is less than that. Okay. And now if you were to substitute instead, I mean, this is equivalent to the lower bound here, right? Because it's just a difference of A bar E versus E. Okay, so that's the proof of those bounds. Okay, I also want to say that if A is symmetric, then A bar is symmetric. That was implicit in the bound that I did earlier, but if you want to see it, if I have 2 unit vectors, E prime and E, then I can write this like that, which is what the same as the calculation on the previous slide. It's just that there's 2 different E's. And now you see that this thing is automatically symmetric if A is symmetric. So that shows you that A bar, because A bar doesn't look like it's symmetric, even if A is symmetric, because we have this formula here, and it's not obvious that this is symmetric. right? Because this parameter E contracts with the A in a kind of weird way, but it turns out to be. Okay, so if A is symmetric, like we have in a conductance model or something, then the sort of effective conductivity of the homogenized material will also, it'll also look like a conductivity. Okay. If the thing is symmetric, then like I said earlier, the bounds I wrote can be written in terms of the partial order on symmetric matrices as just being bounded between two multiples of the identity. And there's a more general fact, which is also implicit in what I wrote above, that A bar is actually between its mean and its harmonic mean. So if you go through the proofs that I wrote back here, you don't actually have to get A bar here. You can actually mess around and get E dot average of AE or something, or yeah, anyway, there's a way in that calculation to recover actually this more general fact, which says that the symmetric matrix is between the harmonic mean and the mean. Okay, actually, did I write this in the wrong order? What is the arithmetic? Which one's bigger? Yes, that's right. The inverse. Yeah. Okay, because there's. Okay, good. Okay, so we can talk more about periodic homogenization if anyone wants. Some people were very interested in this boundary layer that I was talking about. We can talk about that sometime, but I was going to move now to talk about the random case. So how do you get rid of periodicity and what does the situation look like? Okay, so let me move on to that and talk about how you discuss homogenization with random coefficients. So usually when I give talks or courses or whatever, and I talk about homogenization in the random case, I never talk about the qualitative case where you just want to prove a soft homogenization theorem. And then afterwards, everyone comes up and says, why don't you in your course give the qualitative proof? And I say, because it's distracting and I don't like it. But everyone always wants it. And I finally decided that it's actually probably a good idea to do it. So I'm going to give now an explanation of how you do homogenization in the random case. This is essentially stuff that was done around 1980 by 3 different groups at the same time, and who all came up with essentially the same proof. There's the Italians, the Russians, and the Americans, I guess. I mean, I don't know if you call them American, Papa Nicolau and Veradon. Anyway, they're in the U.S. I mean, they're in the U.S. So the group working in the U.S., the group working in Russia, huh? The French didn't write this Courant. Yeah, it's Courant. Yeah, it's mine. I should know. Yeah, is that Courant? Yeah, that's true. Actually, I was having lunch with Veradon last week, and he was telling me about the Ergodic Theorem. So I'm going to talk about that in the next slide. So the setup is we're going to look at the set of all coefficient fields. So I'm going to work with so sometimes when people do this, they work with a very abstract probability space. And I'm going to work with a very concrete probability space in the sense that the set of outcomes are the set of coefficient fields. Okay, so my probability space or my set is the set of all A, which are L infinity functions from Rd, which are valued in the D by D matrices, such that almost everywhere in X, the same ellipticity that I wrote before. Okay. Now I'm going to put a probability measure on this set, and I'm told that in order to do that, I should define what's called a sigma algebra. So I'm going to define the right sigma algebra that I was told to write down. Is you're supposed to write down all the possible random variables that you might want to measure, and that is these. So what I would like to write down is just this. A maps to A of X for a fixed X. That is a random variable, at least if you look at each entry separately or something. And that's basically what I want to do, but I can't really do that, my lawyer says, because these are L infinity functions and they don't take values at a point, and so I have to define my sigma algebra like this. Okay, but whatever, it's the sigma algebra that makes everything I'm going to do measurable, so we never have to discuss this again. But I have this. My jokes are really landing today. It's funny. It's like I haven't given a talk in a long time. On Zoom, people don't laugh like this. So I have omega and F. This is my measurable space. And I'm going to have to do some dynamical systems stuff, unfortunately, in order to talk about the ergodic theorem. So Yeah, as one does, one has to define, yes, if you talk about the ergodic theorem, you have to talk about some group. So we're going to talk, our group is going to be the translation group. So it takes a coefficient field and translates by an integer z. So I take things and I shift them. That is my group, okay? And this TZ, it acts on omega. It can translate coefficient fields, but it also acts on the sigma algebra. I can translate events. Okay, so I translate an event by just basically shifting the whole coefficient field and then talking about the event under that shift. Okay, so this is my translation group. And now I can define a probability measure on this space. And the probability measure basically is just going to be the thing that does the random generation of your field. Okay, so when you pick a sample and look at it, you've just the probability measure has just printed that for you or something. It's like a printer. So, and yeah, so the goal in random homogenization is to never use at least not never, but as rarely as possible use a probabilistic argument. Okay, so we want to never do that unless we really have to, and we will have to at some point. So you want to keep everything, but so I think what you say is you want, we view the probability measure as just giving us NA of X, and once we have NA of X, we can compute stuff, and at some point you take the expectation of something, okay? And expectation is not too bad of a thing. Okay, so that's how I'm gonna think of it. Okay, so I have this omega, this F, I have this translation group. I'm gonna give myself a probability measure on this measurable space. And I'm going to assume it's stationary, and that's, of course, why I had the translation group there. What this means is that the origin is not special from the point of view of the probability measure, okay? The probability measure has to look the same everywhere, and we formalize that with this dynamical systems stuff by just saying that when you translate the set, it has the same probability as if you hadn't translated it, okay? That's it. So I'm going to prove homogenization under only these assumptions. Yes, only. Yeah. What other assumption do you think I'm going to need? I'm not going to assume ergodicity, just because I thought it would be fun for the experts. So I'm not going to assume any ergodicity, and I'm going to prove homogenization anyway. Okay, Scott.
So in particular, you're not assuming translation invariance for non-integers, no?
Right. I'm not assuming translation invariance for non-integers because I don't need to. It doesn't play any role. I could assume translation invariance on any reasonable graph. You could even make the graph be random, and then I would have to work harder. I mean, like this thing is robust to that aspect. That's right. I could have used a hexagonal lattice because we're going to kind of zoom out. So with the fact that you can translate inside of a little cell doesn't matter much. All right, so the P tells us the law of our coefficient field. I think what I'm supposed to say is that this A of X is the canonical coefficient field. And that means that when you have the A of X, you can refer to the A of X, and you know the probability measure gave it to you, and you can let functions depend on the A of X without writing the dependence on the A of X explicitly. So that's what I'm going to do. Is that your okay, so in particular, Jean-Christophe does not endorse that. Okay.
I do endorse that. You're yours.
Okay.
You're grown up.
He's no longer backing up my probability statements. This is bad. Yeah. Okay. So all quantities will be functions of this field. In other words, they're going to be random, and we're not going to be too scared by that. In particular, we're not going to write any little omega or anything like that, because that just serves to frighten people. And has no other purpose. You just have like comma omega. So we're just going to dispense with that. The measurability of all such objects will not be mentioned further, nor will we usually write the dependence below explicitly there. I've said what I had to say. Okay, so now we have the formal setup, and we can do something more fun. Oh, the very, very small font? It says, "My lawyer made me write this." I thought if anyone had really good eyes, they would think that was funny. Yeah, because you can make the text really small on GoodNotes. It's fun. Okay, so the main issue in the random case that we have to do compared to the periodic case is we have to build the first order correctors. In the periodic case, we built them, and we could prove estimates about them immediately because the thing's on a torus and what can happen on the torus. But in the random case, more stuff can happen. So the main issue is, at the first level of approximation in homogenization theory is to build the first order correctors and to try to prove estimates for them. So in other words, sort of the whole theory in the periodic case is going to go over, except for that line. And all of the interest in the random case is exactly what we took for granted in the periodic case. Okay. All the other stuff we did just translates perfectly. Like we can do all of those calculations exactly the same. It makes no difference. Okay. So I'm going to sketch two different proofs. I think that's a lie. I'm really only going to do one because I didn't finish writing the slides for this one, and I was going to do it next time. But I'm going to show you the proof of the sort of the canonical proof using a stationary Helmholtz-Hodge decomposition. It's what it boils down to is some ergodic theorem. Okay, so at some point you need a limit because, and let me describe the issue on the blackboard. So if you want to prove homogenization, you don't have to do this whole higher order expansion, right? You really only need to talk about the first order correctors if you're willing to make errors. And under these very general assumptions, our errors are going to be big. We're not looking at the precision of epsilon 1000. We're looking at little o of 1, just trying to prove a result with little o of 1. Okay, so our expansion with W was like some U plus epsilon times the corrector with slope given by U at the point X. Okay, so we had this. So this whole thing is, of course, a fancy way of writing phi sub gradient of U at X, basically, because the phi is linear in that slot. So you're basically saying just find the corrector with the local slope given by that, and then plug in that with the epsilon out front. Okay, so let me put the epsilon here. Okay, so what we really need for this expansion to be reasonable is we need that this thing be like little o of 1 as epsilon goes to 0. In other words, we need that the correctors, for X in a bounded set, okay? So we need that for X in a bounded set, this expression is going at least to 0 as epsilon goes to 0. And if you rescale that so that you don't have the epsilons there, what you're really saying is that you want that the correctors, if you can define them, to have the property that if you look at the norm in the ball of radius r, and I like to write underlines under my thing there because that just means I put a slash in the integral and then I don't mess up all the computations with volume factors. Okay, so this is like the L2 norm of this with there's a slash in the integral, and then I get to divide by r because there's an epsilon in front, and I want this to go to 0 as r goes to infinity. Okay, so I want to define some solution in the whole space. It's that the wiggles will no longer necessarily be periodic, of course, because it's not the A of X is not periodic. But I want that when I look in a ball, the L2 oscillation is of order little o of r. Okay, so that's what I want to do. So I have to take at some point a limit, right? There has to be a limit coming from somewhere because I need to prove that limit. In order to make a limit happen, I need at this level of abstraction. The things that we call limits are just called ergodic theorems. Like if you have an assumption like this and you prove a limit, then you get to call that an ergodic theorem, right? No. Okay. No. He's burying his head. Okay. So I need to set up some spaces. Okay. So V2 is like L2, but I'm looking at objects which are now vector fields on all of RD and are random objects, so they depend on the A of X. So they're random, they're stationary random fields, which means that the F really is a function of X and it's a function of the A. Okay, but again, we're not going to write the dependence on the A. But stationary means that if I do F of X plus Z A, that it's the same as F of X TZ of A. Translations are working well with the dependence on the coefficient field. Okay, so if it's a random thing that comes from the A, and if I were to translate the A, then I would also, the way that I've defined my F, I would just translate my F. Okay, so there's a way to make it a function of A in a way that is working like you would think it's working. Actually, I wrote it here. Okay, sorry. We're going to norm this by, we're going to norm the set of stationary vector fields by writing that, the L2 norm basically. We're going to take the vector field F and we're going to square it. We're going to integrate, but we're going to integrate over a unit cell in space. And then we're going to take the expectation with respect to the probability measure. Okay. Now I have to integrate over space like this because I said my thing was ZD stationary. So this is really kind of expectation, sort of integration in the probability space, cross integration in a unit cell is the correct, that's the thing that is invariant or whatever. So I have to take them together. Okay. And then I'm going to make a bunch of subspaces. So I have one subspace, which is, I'm going to make a Helmholtz-Hodge decomposition because that's actually that's actually how you build the correctors, is just one application of some Helmholtz-Hodge. In order to do that, I have to make some Helmholtz-Hodge looking subspaces, right? I have to look at the set of potential fields and the set of solenoidal fields. I'm also going to define this thing, which is the set of vector fields which are constant in space, but not necessarily constant in the probability space. Okay, so they're constant in space, and here the y really is over all of RD because now I'm saying I want this to be something which is constant in space. Okay, this one, V2 subscript pot, is the set of potential fields, the subspace of potential fields. So I write that as saying that there's some curl thing. Okay, if you have something if you have a vector field in here, then it's going to be the gradient of something. So it'll be like the gradient of phi. Okay, but you can't necessarily, it makes good sense to write the gradient of phi, but it doesn't make sense to write phi. Because the gradient of phi will be defined, but phi will be only defined up to a constant. Because you know that something's a potential field, but you don't know like what constant to add to it when you integrate. Okay, and there's not necessarily a canonical way to do that. So you should never, if you have a grad, like you're allowed to write grad phi in here. That's kind of abusing notation. But if you do it, that's fine. But you can never write phi. You can never write phi of x. You could write phi of x minus phi of y. That would be fine, because you can figure out what phi of x minus phi of y is by doing by just integrating the gradient. That's well defined. So you can look at differences of 2 points, but not the thing itself. Finally, we have almost finally, we have these solenoidal guys. Okay, and I want to define this thing, which is the guy, which is the orthogonal, the perp of the invariant guys. So these guys, okay, so in the case that this invariant set contains only constants, then the probability measure is ergodic. That's if and only if. And in that case, this thing would be the set of mean zero functions. Okay. Now, if the probability measure is not ergodic, that means that this space can include things that are not just constant. There can be ergodic components, and then in which case this thing will require that your mean zero kind of on every ergodic component. Okay. All right. So this is the setup for a general stationary field. So, as I said, P is ergodic if and only if this is. That's not well. Is that what I meant to write? No, I meant to write constants. I think I meant trivial, but not that trivial. I think I meant to write this, if it can be identified with R. Okay, so usually in homogenization theory, this P is assumed to be ergodic so that this property is true. Okay, and that's actually the definition of ergodic. It's just that this subspace is trivial. Okay, so here is the homogenization theorem. Or okay, this is the existence of the Corrector's theorem, let's say, in this general framework. Okay, so we're going to show the following. Assume P is stationary, not necessarily ergodic, on this measurable space. Then for every E direction that you want to make the corrector, there's a unique potential field belonging to this space. So not only is it a potential, but its mean is zero. Okay, that's what being in here sort of means. Its mean is zero on every ergodic component. This thing basically means that you're not cheating. I mean, when I wrote these wiggles, I really wanted the wiggles to be mean zero. I didn't want the wiggles to secretly be also having another affine function, which takes me totally off course. Okay, so this thing is there for that. This thing is there to keep us honest, basically, to make this thing be mean zero on all the in all the ways that it should be. Okay, so there exists a unique potential such that what? Such that this flux is solenoidal. Well, that being solenoidal means that its divergence is 0, which means that it solves the equation, right? The same equation that we had here. Okay, so that is the super abstract theorem that that I've never presented before. So usually I've never actually seen this thing written before. But this is what you would do if you didn't want to assume ergodicity. Okay. So now what's the proof of this theorem? The proof is I can reduce it to some other statement, which is the Helmholtz-Hodge theorem. So the theorem is, okay, so how do you prove that there are these guys? Well, you build them by Lax-Milgram. By Lax-Milgram, you can build things which satisfy this in the same way that you use Lax-Milgram on the, on the torus or whatever. Okay, so I can build things such that, wait, why did I write grad phi in, no, that's not right. Something is weird. No, this is wrong. The solenoidal field shouldn't be the gradient of anything. This is meant to be, so when I write pot comma 0, I just mean this space. I just don't want to write that intersection over and over again. So I write pot comma 0 for that, okay? So by Lax-Milgram, there exists a unique guy. No, I mixed it. I have this one backward. We're getting to the slides that I wrote this morning now. So I was a little bit tired. Okay. So we have this guy in here. There's a unique one which is orthogonal to all the others, or that has this plus that being orthogonal to all the others. Okay, so you can prove that by Lax-Milgram. The same Lax-Milgram that you can learn, that I learned in the Evans book. So this is really an exercise. Okay, so to conclude, we just need that in order to show, so this thing says that the flux belongs to this V2 pot 0 perp. That's what this identity says. Because you can put the second term, the term on the right on the other side and collect the terms, and it says it's orthogonal to everyone in there, so that's what it means. Okay, so in order to get that it's in here, we just need to know that that actually is equal to the set of solenoidal guys. Okay, which you would expect it to be, right? If you're perpendicular to all potentials, then you should be solenoidal, kind of by definition. But the thing is that we're not defining solenoidal here, like ordinarily, if you define what solenoidal vector fields are, just in L2 in Euclidean space, this is the definition. Okay, but here I'm not making it the definition. I'm making the definition be the thing in physical, in physical space. Like here implicitly what I meant was for every real, for almost every realization of the environment, if you look at the thing you get in space, then it's divergence free in space. I'm not defining it to be the grad perp of the potential guys. So I need to know that those actually agree.
Sorry, just one question.
Yeah.
You know all potential guys are gradients.
I know all, yeah, because I can just integrate because I'm in RD and I don't have any weird topology. Yeah. Yeah, just everything is an RD. Yeah, so I'm willing to do the super abstract probability, but I'm not willing to do any crazy topology. Yeah, just all Euclidean space. Yeah. Oh yeah, but once we build the correctors in the whole space, then we can do the stuff in the bounded domain. By just so like we built the periodic guy. It was in the whole space really, if you want to unfold it, and then we kind of restricted it to the domain after scaling it. So I'll do the same. I'm going to build this in the whole space. And then I'm just going to apply the proofs in the periodic case, and they go exactly. Because I didn't actually use periodicity in any of those calculations, so it just like goes. So what we're missing is this identification between the two ways of defining solenoidal, basically. The two ways of defining divergence free. But yeah, so what are you worried about? You're worried about this thing actually being bigger, I guess. So here's the statement that you need to prove. So the statement that you need to prove is that this entire space is the sort of mean zero potentials, the mean zero solenoidals, and the invariant guys, the guys that are constant in space. Okay, and this is an application of. So I won't prove this, but it boils down to proving this. Okay, if you can prove this statement, then you get this in like a page of argument, which maybe I'll omit because I don't have time. So the way it works is, yeah, so what does the ergodic theorem say at this level where you're not assuming ergodicity? It says that, so now I'm using V1 instead of V2, but I just mean like I define V2, you define V1 just in L1 type norm instead of an L2 type norm. So for every F in V1, you can find an F bar in V1 of guys which are constant in space, such that for every bounded domain, you have the following. Okay, so you have this, which means you take the domain, you scale it up by t, you blow it up, you integrate with a slash, you subtract this F bar like this, and it's 0. So in other words, this thing is converging to something which it belongs to this set, to this invariant set or whatever. Okay, and this happens P almost surely.
Sorry, Scott, did you define V1?
Yeah, so I just said it, I said just orally that V1 is like V2 except with the L1 norm instead of the L2 norm. Yeah, I could have done it with LP, but then I decided to just try to slip that one by you. Okay, so this is the sort of standard Wiener ergodic theorem for, you know, when you have D parameters instead of one parameter. And the point is, if you go through the proof, you don't ever use ergodicity ever, except that when you want to say that this is a constant. So you may as well not assume it. Okay. How do you prove the ergodic theorem? Well, the ergodic theorem is just the same as the Lebesgue differentiation theorem. It's just that you blow down instead of blow up. So you take the proof of the Lebesgue differentiation theorem and you do everything backwards, and that's it. It really is like you prove a maximal inequality, and you all the same bounds are the same, and it's really just a blow down Lebesgue differentiation theorem. So let me state. So you're supposed to stop at 50. Okay. So I need to tie all this together. The ergodic theorem says something about spatial averages of functions. Okay. If you know about the spatial averages of the gradient of a function, then you can recover the function kind of by integration. In fact, if you know about the spatial averages of the gradient, like let's say f was grad phi, and you knew all about the spatial averages of the gradient, then you would know the h-1 norm of that function actually. Okay. So if you kind of translate what this says, not for just integral averages where you're just like multiplying by indicator function of a big domain and then integrating, but instead you try to test with more Sobolev functions, which you can do, then you get this statement, which is the h-1 version of the ergodic theorem. It says that, here I'll specialize to f being in V2. If you look at guys in V2, and you subtract the invariant ones. So if you're in V0, if you're not in here, then you just look at f minus f bar, where f bar is the projection of f onto V2 invariant. Okay, and you subtract. It's like subtracting the mean basically. Like this is mean 0, and the V I in V space is just the set of things with constant. You know, it's the space where the means are. Okay, then you can look at the h-1 norm in a big cube. This notation is my notation for cubes, which will soon come in my next lecture, so I may as well define it here. Just define it's the cube with side length 3 to the n centered at the origin. If you look at the h-1 norm in that cube, where I put an underline here, just like when I underline my L2 norms, I'm making a scale invariant version of a norm that doesn't have volume factors everywhere. Okay, then you get this. So you get that if you divide by the side of the cube and you send this to infinity, then you get 0. Okay, so that's what the ergodic theorem just says for, you know, just in terms of h-1 norms instead of integrals. Okay, now, and I was going to define these spaces. They're defined like this. So you put the underline here when you underline the L2 norms, and then you make a scaling here so that this kind of scales the same as that. Okay. And when you have an underline here, then this norm with the -1 is the same as the dual of the underlined H1. So it's kind of the dual of the so just I'm taking out all of the volume factors basically. Okay, and what do we get? So how do we get the homogenization theorem? Well, so now that if you admit this, the stationary version of the Helmholtz-Hodge projection, then you have solved the corrector equation, And also the ergodic theorem again tells you that you can estimate the size of things like this, because this guy, if you define a bar to be the mean of this sort of generalized mean on every ergodic component, then you can estimate the h-1 norm of the flux, of the difference between the heterogeneous and the homogenized flux. You can also estimate the h-1 norm of the gradient of the corrector, which, as Isabel says, is the same as the L2 norm, actually, of the thing, with the thing here. And that is this. And it's just that I have cubes with size 3 to the m instead of balls with size r. It's exactly that. So basically, this ergodic theorem stated in this h-1 way just is the thing that you want to prove to make the homogenization work in the super abstract setting. Okay. That was a bit fast. I'm sorry. You kind of have to go through the details of this, and it's one of those things where you go through the details and everything's a tautology, and you get to the end and you're like, what happened? Okay. And that's why it's difficult to present, because it's kind of like, where did the proof happen? It's not clear. So anyway, to finish, so now that I have the correctors constructed, we can finish the proof of homogenization by doing by just using this in place of the previous one that was periodic, and everything works. And we prove that homogenization happens with an error that's little o of 1 instead of an error that's square root of epsilon. Okay, so the downside of this super abstract framework is that we sort of lose all the information about the rate of convergence in our homogenization problem, because this term we only know is little o of 1, because that's all the ergodic theorem is giving us, is that it's little o of 1. And so if we want to say more than that, then we need a way to actually study the correctors and to try to bound them and try to figure out how big they are. And that is harder than just proving that it's little o of 1, and requires an argument that's not soft and abstract. Okay, so that's what I was going to explain in the rest of my course, basically. So maybe I'll stop there. Thanks.
Thank you. So are there questions or comments?
Struggling a little bit with your measure.
Uh-huh.
Normally, when you have invariant, you talk about invariant, which is L2. Your probability measure should be more or less on the same probability space, isn't it? In dynamic systems.
I mean, it's possible that I'm using bad notation. I mean, no one's ever written this proof that I've ever found, so I'm like writing the proof. And it's possible that I shouldn't have called it that. But I mean, it's the set of things which are translation invariant for every y in Rd, almost surely in the probability space.
Yeah, then the probability measure you defined on the space value infinity rather than L2, some kind of object.
Okay, so the space, no, the random field can be locally L2, even though the coefficient field A is L2. For example, this thing can be like the gradient of a solution or something defined in some way, and the gradient of the solution may only be in L2, even if the coefficient field is a nice elliptic matrix. So this, I want to allow it to be in L2. I don't know that my correctors are going to have bounded gradients. They can be big, okay? So I do certainly need the integrability to only be L2 here, because these are, when F is equal to A, the coefficient field, or if you look at the rows of the matrix or something, then that's an example of a stationary vector field, but there are more than just the A. And I apply all this theory to Fs, which are somehow found by solving an equation involving A, right? Like I want to apply it to the phis that I make by solving this equation. Phis or grad phis will not be in L infinity.
Yeah, I think I can talk to you later. I'm
Okay.
rather thinking in a dynamic system, you take probability space, you have translation invariant object, then your Ergodic state of the measure is on the probability space you're talking about. You don't change from one to the other one, but maybe
Maybe just to try to rephrase, I think maybe what she's saying is that the standard definition of what an ergodic measure is not exactly the one you're using, because it would not be defined with respect to that specific space. Does that make sense? They would just say, take a measurable set in omega and then it's invariant, and it's not.
But that's
exactly match the.
Yeah, but it's if and only if. You can go back and forth.
But
Like,
I think that's the.
Yeah. Sorry. So I defined ergodicity in a way that's not usually done, but you can you can take an event and then you can translate it around, and then you can call that your field, and then you can see that the definitions are equivalent. Yeah. So most people are used to seeing. Where did I define ergodicity? Sorry, I'll never find it now. But anyway, at some point I mentioned that something was equivalent to ergodicity. Yeah. So this is if you define ergodicity the way that most normal people do, you'll have to prove this, and you can, or you can make this be your definition, because it's sort of, but anyway.
Another question about ergodicity. So because you don't assume it here, is a bar potentially random at the end?
Yes, because a bar is constant in space, but it'll be constant on all the ergodic components or whatever. Yes, it's in that I in V space that I should. If anyone has a better name, let me know. Yeah, thanks.
But it seemed like, I don't quite understand that definition. What it seemed like the previous one was, what it seemed like the previous definition was you're saying that with probability 1, that almost surely F in that space was equal to A of omega, some random variable A, which was just real valued.
Yes, that's right. That's right.
Right. That's right. So in other words, this statement here really should be, is isomorphic to all two of the space of real valued. Yes. Just real valued random variables, not.
Well, a constant. I mean, like if all such random variables are constant, then it's ergodic.
Right.
Yeah.
No.
I'm.
But for
Yeah. I think I'm too tired to understand the words coming out of your mouth. Yeah. It's like I can't. My brain cannot compute the question. I think everyone else understands, but me. Yeah.
So I said a quick question about this. So ideas like this do appear. So in the version of the ergodic theorem that you wrote, you have an explicit representation of the F bar. The F bar is going to be the conditional expectation with respect to the invariant sense. And so, okay, there are versions of things like this where they prove exactly this, where the homogenized coefficient is exactly the conditional expectation of the flux. And basically this classical argument works where the only observation that you need to make is that when you look at these horizontal derivatives on the probability space, it's always the case that the conditional expectation is 0. So I was kind of wondering if you saw if this you also.
I think I'm hiding that in my stationary Hodge decomposition. No. Yeah, you are. But I was wondering. So I haven't seen any of these proofs. Of course, I just sat down with Tuomo and we wrote it, and until it was a proof. And we that's not so I probably am like doing it in a way that's sort of non-canonical. So well, I was just curious, if you're using this fact somehow. I mean, I mean really the proof is somehow like in order to understand the proof, you really have to understand how this implies this. I guess what I mean to say is that somewhere you need to see the connection that the derivatives you're talking about of your stationary fields are induced by the translations defining the stationary. But I don't define those weird weak derivatives on the probability space somehow. I really define everything like with a normal derivative, and so that's what I mean. So I avoid that. Like I'm only willing to do the abstract proof because I don't have to do that. But I know that it's somehow equivalent to what I'm doing, but I never understood that. I still don't understand that. So and I want to stay that way, But anyway, I'm sure that it's equivalent, but I don't. That's quite all right. I'm unable to talk about it because I'm the equivalence. I'm happy to do it your way. This is. But the honest answer is I'm not even pretending. I really am ignorant about how you do. I mean, I get like every time I think about that, I get confused and I think this is irrelevant anyway, and I stop thinking about it. So I don't know the answer to that to your question. Yeah, I mean, I'll show you when we're so Tuomo and I are writing a survey that we've been writing for 3 years and is not done, and it's going to be done next month. Which we've been saying for 3 years. So when it was going to be done before this lecture, and I was going to say, see the thing we just posted, but it's not done. So when I finish it, I'll show it you, and you can say, oh, it's in that line. I think it has to be. It can't be very different from what you're talking about. Yeah, well, yeah, it's basically how you define it. Yeah, because it's these derivatives when you define them, it's a stationary field, and if you everything's a tautology. Yes. I was just curious because you have this like local version. I mean, the only thing that's not completely obvious is this ergodic theorem. And then everything else you realize is a tautology, right? The ergodic theorem, like the Lebesgue differentiation theorem is not obvious. But everything else is like move the definitions around. And calculation is really like, to go from here to here, you have to like to show that if this weren't the case, then you can witness the failure of something to be solenoidal in a stationary way so that, anyway, it's some nonsense. Anyway, let's talk. We can maybe talk about it more.
Other questions?
So, well, I'm a probabilist and I feel Oh, I don't feel comfortable with the ergodic theorem as well, so I think it's okay if you don't like it. At the end of the day, the only important thing is your Helmholtz decomposition theorem, right?
Yeah, I mean, like I said, this is like a way of writing the ergodic theorem in a way that's nice for us. Sorry that I swept that under the rug, but I didn't have the heart to try to prove that on the.
So you mentioned that with variational principle, you can also avoid the stationary Helmholtz Hodge theorem.
How would you avoid the stationary Helmholtz Hodge?
Yeah.
You would just not prove things in this soft of a way, or you would do a variational argument and not try to build the correctors in the whole space.
Okay.
Okay, like really you don't need to build the correctors in the whole space. That's silly. Like you need to build them in the region that you're trying to solve the problem in. And so you build them in that region, and you discover at the end of your proof that it was all equivalent anyway. And if you do it in that way, then it's more concrete, and you can actually do it more easily, in my opinion. But this proof is the sort of the canonical one with some twists of our own. But the one I was going to do that I'll probably sketch at the beginning of the next lecture is the variational one.
Okay.
So that's the one that I usually do. I'm doing this one like to be different this time.
There for the questions, comments. Okay, so if not, then let's thank Scott again.